Electric current is the rate at which charge passes through a cross-sectional area over time. This flow is represented as I equals dq over dt. This is a basic closed circuit. It contains a power source, a resistor, and a steady loop of current moving through the system. To understand the behavior of this circuit, we must measure the potential difference, the voltage, across the resistor. A conventional voltmeter is the standard tool for this task. To measure the potential difference, the meter must be connected in parallel across the component. This parallel connection creates a new path for the charge. Because the voltmeter has its own internal resistance, it inherently draws a fraction of the current away from the main circuit. The resulting readout on the meter is lower than the true theoretical value of the original circuit. This is a measurement paradox. You cannot observe the circuit with a standard tool without changing the total resistance and current of the system itself. Solving this requires a different approach, the null measurement method. The goal is to engineer a system that can determine electrical properties without drawing any current from the host circuit. Gustav Kirchhoff established the foundational laws of conservation necessary to analyze multi-loop networks. His first law, the current law, states that the algebraic sum of electric currents at any junction is zero. This is a statement of the conservation of charge. There is no loss or gain of current at an intersection. His second law, the voltage law, focuses on the conservation of energy. In any closed loop, the algebraic sum of the EMFs and the potential differences across each part of the circuit is zero. These laws are applied to the Wheatstone bridge, a network of 4 resistors, P, Q, R, and S, arranged in a quadrilateral. A sensitive galvanometer connects the center nodes, B and D. Using sign conventions, we trace the first loop, A, B, D, A, to sum the potential changes into a first equation. We then trace loop B, C, D, B to form a second equation. Tuning the resistors balances the bridge, so the galvanometer reads 0, removing its terms. This reveals the mathematical proof of the bridge. When balanced, the ratio of P over Q is equal to the ratio of S over R. Because no current flows between B and D, those 2 points are at the same electrical potential. We have extracted an exact resistance ratio without creating a disruptive crosscurrent. This theoretical network is applied in the laboratory through a device called the meter bridge. The meter bridge uses a uniform 100 centimeter wire. An unknown resistance X and a known R connect via a sliding jockey. Sliding it adjusts the resistance ratio. At the null point, the galvanometer shows 0, giving lengths Lx and Lr. Resistance is proportional to length. For a uniform wire, we swap resistance values for physical lengths. This gives a workable equation. X over R equals L minus X over L minus R. Knowing the lengths and one resistance, the unknown X is calculated precisely. For this to be accurate, the wire must be perfectly uniform, so the resistance per unit length remains constant across its entire span. The value of R is chosen so the null point falls near the center of the wire, which minimizes errors caused by the contact resistance at the end strips. Sir William Thomson, also known as Lord Kelvin, used these same principles to develop a method for determining the internal resistance of a galvanometer. Standardized equipment like this antique resistance box allowed scientists to dial in the exact known resistance values required to reach the null point. The meter bridge solves the measurement paradox by translating a physical distance into an uncorrupted electrical value. While a bridge measures resistance, measuring pure electromotive force requires a different instrument, the potentiometer. A potentiometer consists of a long, uniform wire connected across a dedicated battery. The device operates on the principle of potential gradient. Because the primary current and the wire's resistance are constant, the potential drop along the wire is linear. The potential gradient, K, is simply the total voltage divided by the total length. Consequently, the potential difference between any 2 points on the wire is directly proportional to the physical length of the wire between them. By establishing this linear ruler of voltage, EMF can be measured without drawing any current from the cell being tested. To compare 2 cells, we first connect cell E1 to the potentiometer and find the null point. This gives us a balancing length, L1. In this state, the EMF of the cell is equal to the potential gradient multiplied by the length, E1 equals K times L1. We then repeat the process with a second cell, E2, to find a knee balancing length, L2. Dividing these two lengths gives us the exact ratio of the two EMFs. These same principles are used in modern laboratories to find the internal resistance of a cell. Calculating internal resistance requires comparing the cell's EMF when no current is flowing against its terminal voltage when it is part of a closed circuit. The potentiometer finds the balancing length for the EMF, and then a second balancing length after a resistor is connected across the cell. These two lengths are used in the final equation. Internal resistance, R, equals R times the quantity of L1 divided by L2 minus 1. Unlike a standard voltmeter, the potentiometer draws zero current from the test cell at the moment of the null point. It functions as a meter with infinite resistance, measuring the potential difference without interfering with the original circuit.